All right, in the next part of the section 4.7 material, we'll look at some applications, some applied problems of finding a maximum or minimum of a function of two variables. So in this next example, we are asked to find three numbers whose sum is 60 and whose product is a maximum. So let's start by introducing the function that we're trying to optimize. In this case, we are asked to maximize a product of three numbers. So let's say that our function that we're trying to optimize is x times y times z. It's a function of three variables, which are my unknown numbers. And I'm told that the sum of these numbers is 60. So x plus y plus z must equal to 60. Now, this function f that we have is a function of three variables. And so far, we've only been working with optimizing functions of two variables. But what I can use here is the constraint about the sum of these numbers being 60. If the sum of the values is 60, then I know one of the numbers, let's say z, is equal to 60 minus x minus y. And I can now take this expression for z and substitute into the function f to get it in terms of just x and y. So here, our product would be x times y times z, which was 60 minus x minus y. Or if I distribute, we have 60xy minus x squared y minus xy squared as our function. So now, in order to maximize this function, we need to start by finding the critical points of our function. And recall that the critical points are found by setting our partial derivatives of the function equal to 0. So here, we'll start by looking at the partial with respect to x, which is 60y minus 2xy minus y squared. We set this to 0. And our partial with respect to y, which is 60x minus x squared minus 2xy. We also set equal to 0. So if we look at our first equation here, we notice that we could factor out a y from each term, and we're left with 60 minus 2x minus y is 0. And in order to maximize our product of these three numbers, we know that we would not want this first term, y, to equal to 0. Otherwise, the product of our three numbers would be 0, which is going to be the minimum value that our product could take. Now here, that means if y is not equal to 0, that the expression in parentheses, 60 minus 2x minus y, has to be 0. And we find that 2x plus y has to equal 60. Now, in a similar way, if we look at our second equation for the partial of f with respect to y, we see that we can factor out an x, and we're left with 60 minus x minus 2y is equal to 0. Now, using similar reasoning, we know that we do not want x to be 0 in this case, because that would minimize the product of our three numbers rather than maximizing it. So instead, we need 60 minus x minus 2y to equal 0, and it follows that x plus 2y is equal to 60. So in order for this function to have a critical point, we need both of these equations to hold. So let's consider that system of equations. Here, our first equation was 2x plus y, which has to be 60. And our second equation is x plus 2y equals 60. So there's a number of ways that we could go about solving for x and y in this system. My personal preference would be to take my first equation and multiply through by a factor of 2, and then subtract these two equations to eliminate the variable y. So what I'm left with is 4x minus x, or 3x, is equal to 120 minus 60, or 60, and therefore x is equal to 20. Now once I have x, I can substitute into either one of my earlier equations to solve for y. My first equation says that y is equal to 60 minus 2x. So if x is equal to 20, we find that y would also be 20. So we have x and y need to be 20 in order to maximize our function, and we still need the value of z. Now if x and y are both 20, then we find z, which was 60 minus x minus y, would also be 20. So here we find the points of interest, x, y, and z, would all need to be 20 in order for the product of those numbers to be maximized. All right. So in our next example, we will look at a similar problem. It's maybe a little more practical. We are asked here to find the maximum volume of an open rectangular box that has a surface area of 75 square meters. So let's say we have 75 square meters of cardboard or whatever material to make our box, and we want to know what is the largest volume of a box. So here, let's maybe start by visualizing our box that we're building. We have some open rectangular box and open here, meaning that it does not have a top. So bottom and 4 sides. So the dimensions of this box, let's label as x, y, and z. And we're trying to maximize our volume of this box. So let's introduce the function that we're trying to optimize. In this case, v for volume would be x times y times z. And we're told that the surface area of our box would be 75 square meters. Now here, for an open box, a box without a top, we would add the area of our sides. So starting with the bottom, we have the bottom with an area of x times y. Then for the front and back of this box, each has an area of x times z. So we have 2xz for the front and back. And then for the left and right hand sides, we have 2y times z. And we know that this surface area must equal 75. So as we did in the previous example, we can use this constraint on the surface area to solve for z and get our function for volume down to a function of just x and y. So here, if we start by subtracting xy from both sides, we have the following. And on this left-hand side, I notice I can factor out a z, which leaves me with 2x plus 2y is equal to 75 minus xy. So solving for z, we have 75 minus xy over 2x plus 2y. So taking this expression and substituting it into our function for volume, we have the volume v is x times y times z, which we found to be 75 minus xy all over 2x plus 2y. Or if we distribute the x times y through the numerator, we have 75xy minus x squared y squared all over 2x plus 2y. So now, in order to maximize our function for volume, we need to start by finding its critical points. So let's start by looking at the partial derivative of volume with respect to x. So here, making use of the quotient rule, the derivative of our numerator with respect to x is 75y minus 2xy squared, and then we multiply by our denominator, 2x plus 2y. Then we subtract our numerator, 75xy minus x squared y squared, times the derivative of the denominator with respect to x, which is 2. And then the whole thing is divided by the denominator 2x plus 2y squared. And we set this partial derivative equal to 0. Now we know that the only way a quotient can equal 0 is if the numerator is 0. For instance, we could multiply both sides by our denominator. So if I were to expand this numerator, we have 150xy plus 150y squared minus 4x squared y squared minus 4xy cubed minus, if we distribute this factor of 2, we have 150xy minus 2x squared y squared. And this needs to equal 0 in order to give us a critical point. So here we see that some terms will cancel. We have a 150xy minus 150xy, which will cancel. And then we can combine our negative 4x squared y squared with a 2x squared y squared. And we're left with 150y squared minus 2x squared y squared minus 4xy cubed has to be 0. So I notice that from each term in this equation, I can factor out a 2y squared, which leaves me with 75 minus x squared minus 2xy is equal to 0. So again, if we're trying to maximize the volume of this box, well, we know that we don't want this first factor of y to be 0. Otherwise, we would have a box of 0 length or 0 volume, which of course would be the minimum volume for our box. So if we're interested in the maximum, we know that this expression in parentheses has to be 0. So we find 75 minus x squared minus 2xy is 0, or equivalently, x squared plus 2xy has to equal 75. Now this was just the condition that we have by setting the partial derivative of v with respect to x equal to 0. Now to save ourselves a little time, we find that if we were to differentiate this function with respect to y and set that partial derivative equal to 0, we arrive at the condition y squared plus 2xy has to equal 75. So it's the same sort of condition that we had by setting our partial derivative of v with respect to x equal to 0. If we take our partial with respect to y and set it to 0, we find that the following must be satisfied. So in order to find the critical points of our function, we need both of these equations to hold. So let's consider that system of equations. So here, we are considering the system x squared plus 2xy is 75, and y squared plus 2xy is equal to 75. So to solve, we could take the difference of these two equations, and we find that x squared minus y squared has to be 0. Therefore, x squared is equal to y squared. And since x and y are the dimensions of a box, they both have to be positive numbers, so we know that x has to equal y itself. So now, once we know that x and y are equal to each other, we can look at our two equations and set x equal to y, and we find x squared plus 2x squared is 75. So 3x squared is 75. X squared is then equal to 25. And so x is 5. Now, since x and y have to be the same, y is also equal to 5. So we found two dimensions of our box. Its length and width need to be the same. Now we need the height of our box, the z value. So let's look at our work so far. If x is equal to y, which is 5, then we found that z had to be given by 75 minus x times y, which would be 25, all over 2x plus 2y. So here we would have 20, and we're left with 50 over 20, or 5/2. Now the problem asks us for the maximum volume of such a box, so to find the maximum volume, let's call it V max, we would take the product of x, y, and z, and we're left with 125 over